Hello, this is Dr. Strickland. In this video, we will investigate some general mechanisms and also begin our conversation about the reactions of carbonyl compounds with carbon nucleophiles. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. So I wanted to briefly compare the kind of mechanisms that you'll see with aldehydes and ketones against what you have seen with carboxylic acids, because the carboxylic acid derivatives undergo a reaction that's called nucleophilic acyl substitution, where the nucleophile attacks the carbonyl carbon, forms a tetrahedral intermediate, or maybe two, and then the least basic group is eliminated as the carbon-oxygen double bond is reformed. Aldehydes and ketones are different. With strong nucleophiles, they undergo a reaction type called nucleophilic addition, where you form that tetrahedral intermediate, but then you get a protonation. You don't get the reforming of the carbon-oxygen double bond. If you have aldehydes and ketones with a weak nucleophile, you get something called nucleophilic addition elimination, where when the nucleophilic atom is oxygen or nitrogen and acid is present. In that case, you have a tetrahedral intermediate. And instead of it being protonated and just stopping there, it ends up being dehydrated. And you form a new pi bond, but it's not necessarily a carbon-oxygen double bond. So we'll see those as time goes by, but I wanted you to have all this just in one place where you could see the comparison. Okay, so the strongly basic nucleophiles are these. It's all the carbon nucleophiles. And a hydrogen nucleophile. So the Grignard reagent, the alkyl lithium, the alkynide ion, and then the hydride ion. We will have a cyanide ion, which more belongs down here, but doesn't exactly belong either place, but we'll talk about it when we get there. Although the nucleophiles that are weaker bases are protonated: water, alcohol, ammonia, and primary and secondary amines. So just to sort of sketch out a general way to represent these guys, I'm gonna do like this. So this can represent either an aldehyde or a ketone. We'll let this R prime either be the other alkyl group of a ketone or the hydrogen of an aldehyde. Because aldehydes and ketones undergo many of the same reactions. All right, so if this guy attacks the most electrophilic place, it would attack the carbonyl carbon and send the electrons up onto the oxygen. That gives us a tetrahedral intermediate that looks like this. Now, the reason it doesn't eliminate and reform the carbon-oxygen double bond is because none of these would be very weakly basic. Certainly, I guess you could go back to where you came from, but other than that, there are no good options. So instead, we find that aqueous acid usually is used to deliver a hydrogen cation, and so this is just an acid-base reaction, just a protonation. And what you make is an alcohol. Now, this other kind of reaction has a bunch more steps for sure, but it starts the same. Again, we're going to use this general structure that can represent either an aldehyde or a ketone. And now we'll use this more weakly basic and protonated and neutral nucleophile. Same kind of nucleophilic attack. And so then we have a tetrahedral intermediate that looks like this. And there are going to be two charged atoms here. The oxygen is one of them, and this Z, whatever the nucleophilic atom was of the nucleophile, so it will either be an oxygen or a nitrogen. And then 3 steps, and we're not going to delineate those right now. but you get a protonation here, a deprotonation there, and then another protonation here. So that we've got something that looks like this. And then we get the formation of a pi bond here and the loss of water here. And that gets us to this. And I'm just going to leave it kind of upside down at the moment. Like that. And so you know that water came off here. Okay. All right. So we're going to start with Grignard reagents because they are probably one of the most common carbon nucleophiles. And so down here, what I've got is separated now. The general reaction pattern for a Grignard with aldehydes as opposed to ketones, so that you can see that, like here, for example, that if I have an aldehyde with one alkyl group, and so here's the alkyl group of the Grignard reagent. One Grignard adds to one molecule of an aldehyde, and you get both of these guys in there. And so we have formed a secondary alcohol. All right, so I'd like you to look at this sample problem over here. And so pause the video, draw the structure of the product, and then come on back. All right, welcome back. So this is the R group that's attached to the carbonyl carbon of the aldehyde. This is the R group that's attached to the magnesium. And remember, it's this carbon that has the partial negative and is actually the nucleophilic atom. So I'm going to draw this like that. So you can see that the new piece came in here. Yeah. Okay. And so it may not always be written like that, right? You could just do the whole thing left to right. So I'd like you to pause the video and write the name of this product and the name of the starting aldehyde too. Do both of them. Pause the video and do those two names and come on back. All right, welcome back. So this is butanal with 4 carbons. And this guy, 1, 2, 3, 4, 5, 6. This is six carbons in the parent. The OH is on carbon 3, so this is 3-hexanol. And because every carbonyl carbon is sp2 hybridized, it has trigonal planar geometry. And so if this is an asymmetric carbon, and it is in this case, you're going to have RNS stereoisomers. All right, come on down here to ketones. Ketones, we've got 2 alkyl things that may or may not be identical. And then a third one here. So when this attacks the carbonyl carbon, you can have as many as 3 different alkyl groups attached to what used to be the carbonyl carbon. And now instead of making a secondary alcohol, this makes a tertiary alcohol. All right, so I want you to use this general reaction pattern, draw me the product, and then write the name of the starting compound and the product. And then come on back. All right, welcome back. So this is the carbon piece that's going to attach right there. So this is cyclopentanone. And this is 1-methyl 1-cyclopentanol. And both of those ones should be optional. Now, could you have RNS enantiomers here? No, because this is not an asymmetric carbon. Okay. All right. So let's take a quick look at the mechanism because it's very short and would be the same whether you were talking about a ketone or an aldehyde. So I'm going to do it this way so it will represent both. So the carbon is directly bonded to the magnesium, uses the electrons in the carbon metal bond here. And we get nucleophilic attack like this, which gives you that tetrahedral intermediate. Like that. And since carbanions are crazy basic, nobody can be kicked out. You may see the second step as hydronium ions, you might see it as aqueous acid like HCl in water. So this is a protonation. So a nucleophilic attack followed by a protonation. Water comes off. And get your alcohol. All right. So that is the basic story on what the general mechanisms look like for these two different kinds of reactions of aldehydes and ketones, and the beginning of using Grignard reagents. If you have any questions, please send them to me.